Hi, this is continuation for power electronics lectures, and today we are going to cover power transistors. In the previous lectures, we have covered the diodes, types of diodes, and how we connect them in series and parallel. And also, we consider talking about a little bit of how they use different materials like silicon carbide and GaN to present for us or introduce to us some different properties and features, making them dominating the market so far. So the transistors in general, they are classified as bipolar transistors, MOSFET, and IGBT. And I think you know these classifications from electronics modules before. And the bipolar transistors, they are classified as small signal transistors using for the general purposes and high speed switching and communication application and circuits. And we have also power applications, and maybe our concern now is about power BJT or bipolar transistors. And also some of these transistors can be used for logic and digital circuits. It's not our target today, but we have also another category of transistors, which are the MOSFETs and IGBT for power as well. Okay, so we'll not consider talking about a small signal and general purpose transistors, but we will focus on just power transistors. And today our lecture is starting talking about bipolar transistors or BJT transistors. So how they are different and what they bring to us for power circuits. So the BJT transistors, usually we have PNP and NPN transistors, and these are the symbols. The construction, as in the diode scenario, they have introduced new layers with different properties and different doping percentage, and the same happened also for transistors. So we have here N positive, okay, metal, okay. They make different construction as well. Instead of a planar connection, they have separated that. I will not go deeper into that one because it's not my interest, and also it's not the focus of this module. Okay, so the material side here and the construction inside these transistors is not something that we want to go into details. But in general, the power BJT transistor, they bring to us transistors with less gain. So it's not like hundreds of gain. Okay, it's just maybe tens to few of tens of gain. Okay, and in power electronics, we don't care really about gain. Okay, we care more about how we switch it on to put it in saturation, or switch it off to put it in cutoff very quickly. Okay, so we will not use it for amplification. Okay, but we have to use that gain just to design the switching circuit. And if we look at the switching, I think in the switching losses we talk generally how these transistors switch on and off. Okay, so if we have the circuit, for example, we have this transistor and we have a load and supply. We can control the current going through that branch by controlling the current going into the base. Okay, so by supplying voltage here on the base, okay, positive voltage, for example, okay, that positive voltage will push some current, which is I base. Okay, that I base now will control the current coming from the collector, okay, or into the collector, and that will take some time. First time is the delay time, and then the rise time, and we call this one as the on time switching. Okay, so we have mentioned that before. I think you know what's the delay time and rise time. And after that, it will go to the conduction period, the on period. Okay, and then to keep it in the on period here, you have to keep supplying current for the base. Okay, and when you decide to turn off that transistor, you have to supply maybe 0 volt, and better, you have to supply negative volt. Why negative volt? Because we have some charges here, exactly like the diode. We have some charges in the junction, and we want to remove these charges very quickly. Okay, to remove them very quickly, it's not enough to apply 0 voltage. No, you have to also to reverse the current from the emitter to the base and going out. Okay, to reverse the current, you have to apply negative voltage, and that's very common in many switches. Okay, after applying negative voltage, the current will reverse, the IB will come out from the base, and now the switch now is going to turn off. But we have some delay. That delay is caused because of the storage time. We have some charges need to be removed. Okay, that takes time. And also we have the fall time. So that's the general switching pattern of BJT transistors. And if we have spoken about it a little bit in detail, so I think we know this curve, okay? The I base and IC. So now if the I base is 0, the collector current will be also 0, okay? Now if I start increasing I base more and more and more, the IC also will increase, and we are now in the active or linear region. After that, we have a region where we have I base, okay, supplying that current, which is ICS, the saturation current. If I increase more and more and more I base, this will not increase the collector current. Again, we can also provide another figure, but this time is Vn and VCE. VCE now, which is the collector to emitter voltage, will be very high if the switch is off, okay, and very high to the value of VCC. This is the cutoff region. And if I want to turn it on, I have to supply current more and more and more, and the voltage across this transistor will be dropped less until it goes to the saturation where we have VCE sat. So this is the curve for the voltage, and this is the curve for the current. Again, we have active region between them, and that active region is controlled by this equation. I collector, the current in the collector is controlled by the gain of that transistor multiplied by the I base I'm pushing into the base, and we know that. But in the saturation or cutoff, this one is not applicable, okay? So the purpose in power electronics, we have to go from cutoff to saturation, and from saturation to cutoff very quickly, okay? So to do that, if I have a current, for example, I have 100 volts here, I have 100 ohm, so the current going through the collector, if it's fully saturated, is about 1 ampere. So if I know that 1 ampere as IC, I can use beta from datasheet, and I can estimate what is the base current I have to push here into the base to get that IC, okay? So I can use this calculation to choose the IC, and also finally I can choose IB. That IC is called IC saturation, which is 1 ampere for our example, and I can use beta, and that base current that causes the saturation is called IBS, IB saturation, okay? That causes the saturation. And that base current, actually, it will be at the edge of the active region and saturation region. So to be at that corner exactly. Now, are you happy with that position here? I think we will not be very happy, because now we might go to the active region and we dissipate more heat, and we want to be more in the saturation region. To push our transistor more in the saturation region and to push it there further, okay, we have to supply different current. That current is a little bit more than the IBS, okay? So if you raise that current, the IBS, to different value, which is IBF. IBF is the forced base current. So if the saturation current, for example, 1 milliamp, but I supplied 5 milliamp, that means I forced I base to be 5 times the saturation or the calculated one. Why? Because I want to push it in the saturation more. So what's the point of saturation more? That means VCE sat will be less, because if you push it to saturation more, the VCE sat, it will be less. That means less conduction or less conduction losses, okay? But there is some other drawbacks. I will talk about it later. Now the ratio of IBF and IBS, how much I increased the IBS to be IBF, is called the overdrive factor. I overdrive it. I can drive it by IBS, but I overdrive it by supplying IBF, which is the forced IB. The ratio between them is called overdrive factor. And if you are looking at this equation again, you have ICS and you have IBF. The ratio between them is not beta. There's a different factor, and we call that factor is the forced beta. So we have forced B, and that beta is not anymore the beta that I got from the data sheet. No, it's a different one. Okay, the knowledge of forced beta is not really beneficial. So it's just for calculation, just to know how much you consider your beta. Okay, so this is now how we drive our transistor and how we supply different value of base current to overdrive it and to push it into more saturation. But again, pushing to more saturation, that means lower VCE sat, yes, but longer turn off time. If I'm now in the saturation here, I have to go back all that distance to turn off. But if I am here, I just go shorter distance, okay? So that means in the overdrive scenario, I have to remove more charges before turning off the transistor. We have another thing, but it's not related to overdrive factor. It's something different, which is it might lose the saturation if the load changes. Now I designed my saturation now and my I base to saturate the 1 ampere. But if that 1 ampere is different now, I make the load different. Okay, it's higher. So it might be now 10 ampere. Is the I base that I choose and designed able to saturate it? The answer might be no, and we will be in the active region. That means higher dissipation and higher heat. Okay, so that's why we avoid using BJT, because the driving scenarios is a little bit complicated than the other transistors like MOSFET and IGBT, and we have some complication in driving and calculating the driver circuits. So let's have now an example. We have a bipolar transistor, which is this one, is specified to have a beta, but that beta from datasheet is not one specific value. Sometimes in the datasheet they give us range of values in the range of 8 to 40. Now the load resistance is 11 ohm and the VCC is 200 volt and the V base, which is this one, okay, is 10 volt. Now if the VCE sat is 1 volt, the voltage across the transistor in the saturation is 1 volt, and the VBE sat, the voltage across this junction here in saturation is 1.5 volt. So find the value of RB, which is this one, how much I should choose it, that results saturation. So I should push it into saturation and passing the current there, but I have to overdrive it also with factor of 5. So let's now look at the circuit and analyze this branch. Okay, I think we have to write the equation first for this loop. The equation will be the voltage of the base minus the voltage drop across this resistor minus the voltage across this junction equals 0. Okay, and if you just manipulate that, you will have the RB value equals the V base, which is this one, minus the VBE sat, because we are talking about saturation scenario, divided by I base that I want to push. Okay, now I don't know RB and I don't know I base. I know VB, which is 10, VBE sat, which is 1.5, but I don't know IB. What is the IB that causes saturation for my transistor? To know that, I think we should look at the collector curve first, because I don't know the collector curve to select IB. Okay, so the first thing is to look at the saturated collector current. In saturation, the ICS equals VCC minus VCE sat divided by RC. This is the equation for this loop. Okay, VCC minus VCE sat divided by RC. I know all the values for that one, and that gives me IC saturation is 18.1 ampere. I know IC, I can use beta now to calculate IB, but beta now has no just one value. It has range of values, 8 to 40. Which one should I choose? Now, in the worst case scenario, you should choose the lower gain, because we should consider that our transistor is not able to amplify I base to generate IC. Okay, so if we consider 40, that means we are looking for very healthy transistor, but 8, it will be considerable for worst case scenario. So in the worst case scenario, the beta minimum is considered here to give us the value of I base to cause the saturation, given that the ICS which I calculated here. So by knowing this, I think we know the IC divided by beta minimum equals IBS, and that will bring to me 2.26 ampere. So I have to push into the base here 2.26 ampere. But this brings me at the edge of saturation. I have to push it more into saturation by providing overdrive factor. So it's given here the overdrive factor is 5. That means I have to multiply this value by 5, and that will generate 11.3 amp. It's very high value to push it to the base, but this is just for the example, okay? So we have to push here after overdriven it 11.3 ampere. I know now the base current that I should be pushing, okay? So now after knowing all the other values, I think the value of RB will equal 0.75 ohm. So this is the design of the circuit. The second requirement is, what is the forced beta? I know this beta is 8, okay? But after overdriven it, I have different beta, and that beta is beta forced, okay? I know the equation for beta force, which is ICS, which is this one, but divided by not IBS, is divided by the forced voltage, okay, which is this one, okay? After making the ratio calculation, it will be 1.6. So it's not 8 anymore, it's 1.6. This is what is considered in my circuit. So the last one, what is the power loss by this transistor? Remember, the power loss by this transistor will be finally dissipated as heat. And the power loss is not just across this terminals, which is collector to emitter. No, it's also across the base to emitter junction, because we are pushing 11.3 ampere here, and that 11.3 is very high, and it will go through that junction, okay? So now the power losses will be the current going through that transistor through that route multiplied by that voltage, which is VCE sat, and also the current going through that route multiplied by the junction voltage, which is VBE sat. So the equation is VCE sat times IC plus VBE sat times IB, okay? And you should select IC saturation and IB forced, because we forcing the I base to be that value. So now after multiplying and after calculating the equation, it will be 35 watt, okay? So this is the losses for this transistor. So the last part in this lecture is talking about driving BJT transistors. And the word driving means how we switch it on completely and how we switch it off completely, okay? And in a fast manner. So what is the driver? The driver is a circuit that has low output impedance. Low output impedance, that means it can source, give high current, and also sink, absorb high current, okay? That is able to source and sink relatively large current. That high current, as we mentioned before, it will be pushed to the base to turn it on very quickly and turn it off very quickly, to achieve high switching speed, to decrease switching losses, because I don't want to spend more time in the active region. And for example, we have this circuit, we have this transistor here, okay? And this is the driver circuit there. And that driver circuit is responsible to generate for me a curve like that. It needs to push current with a peak like this, okay, into the base, to switch it on very quickly, and also to absorb all the charges in the junction very quickly by supplying negative current and voltage, and also absorb all that charges to turn it off completely, very fastly. So the definition of the driver is common between BJT transistors and also other switches. So we have this circuit, for example, okay, is gotten from one of the references in the reading list. We have circuit here, and that circuit give us positive voltage and negative voltage, okay, and by this circuit now it gives us a peak value here of current at exactly the on time when we apply the pulse of on time, okay, and that peak current give the transistor a push to go to the on time very quickly, and also there is a negative peak current here to remove all the charges and to turn it off very quickly. So how we actually supply that peak voltage here and peak current, okay, it's by using this capacitor. We know the capacitor at the first instant it will work like a short circuit because it doesn't have any charge and it will absorb all the current very quickly. So when you supply the voltage in positive here, that voltage and that current will go, and you'll find here a resistor and a capacitor. That capacitor works like a short circuit at the first instant, so it will go like that and will push all the current through the base. So that's why we have a very high peak here. But after that, the capacitor will now start decreasing the current going through that branch because it's now approaching to be charged or fully charged, okay? And the current will have another way to go, which is through the R2, okay? So during this time, it goes through R1 and R2, but during that time, it goes through R1 and C1. This is one of the tricks they use to push like instantaneous current into any other circuits or other terminals. And when we supply this, the negative voltage, it peaks also, but in negative, okay? And we got this negative one to make the switch off very quickly. Now we can supply the positive voltage and negative by another circuit, which is look like this one, okay? This one is called totem configuration. And when we supply here positive 5 or 0, okay, 5 and 0, 5 and 0, so the 5 volt will turn on that transistor and makes positive voltage to go to that point here, and makes also pushing a spike of current to the base, okay, this one. And when we turn off that transistor, it will turn on that transistor, which is PNP transistor. Negative voltage here makes the current goes out from the base through that capacitor first, and then go there to the negative voltage here, or 0 voltage. It's better to be negative, okay? And that will deplete all the charges very quickly and turn it off. So the BJT is a current control device. This is one of the problems, okay? It depends on the current and peak of the current to turn on and off. It's not like the MOSFET or IGBT. The base current peaking can reduce the turn on time. I'm talking about this. The reversing the base current, which is this one, can reduce the turn off time. And the storage time, the TS, when we turn it off, of the BJT increases with the base drive current and overdrive. We mentioned about overdrive, but when we overdrive and push it to saturation more, we have to return back by removing all these charges and go back to turn off. If we overdrive it more, these charges will be more, and we have to go back also by removing more charges than before, and the turn off time will be bigger, okay? That's why we have this concern. Now, the last thing is, if you want to connect parallel BJT transistors. Now, we connect parallel BJT transistors because we want to increase the current capability. And this is one of the scenarios, okay? That current, okay, go through that transistor, and that transistor, and that transistor. They are connected, collectors together and emitters together. Is this the right way? The answer is no, because this will not guarantee equal current sharing, because there are some mismatches between in the process of manufacturing. And the current mismatch, if that one maybe now going through it is about 1.5 ampere, this one 1 ampere, and this one half ampere. So the 1.5 ampere going through that transistor will heat it up more than others. And the problem with BJT transistors is the conductivity relation with the temperature. The conductivity increases with the temperature, and this is the problem. So the first one, if it conducts more current, it will heat up more and will increase the conductivity that makes it conduct more current than others. So the 1.5 ampere will turn to 2 ampere, and then to 2.5 ampere, and then to 3 ampere, okay? And that's the thermal runaway again, okay? Because there is a property in the BJT transistors called the negative temperature coefficient characteristic, okay? That's one making the temperature rise, causing more current going through that transistor. And that will lead to be more current and more heat and then thermal runaway. So this is the problem of this scenario. How we solve that? By introducing these sharing resistors at the emitters here. And by going through that scenario, I think we're talking about the same solution for paralleling the diodes, okay? By going through that one, the sharing the current using the emitter resistor, these resistors can actually control how much current going through each branch to be closely to each other. And also is a good practice to share one heatsink for all these transistors and to make them very close to each other. Because if one heat up, it will share with the adjacent transistors the same heat, and they will increase and decrease all together, and makes also good sharing between themselves. And this is one of the pictures, just an example of what I'm talking about. So that brings me to the end of this lecture. I hope you enjoyed it and you get more information about transistors and how we drive them and connecting them. Thank you very much, and see you in the coming videos.